So also having bits of class reunions now as well. So, let's move on. All right, I mentioned a couple of slides ago about how we're mainly just dealing with fairly homogeneous structures, that we are essentially just making pretty simple geometries. And even there, we're having difficulty in understanding and controlling the cellular regenerative processes. And a lot of people now, I've talked to quite a few people over the last few days who ask about this word vascularity. And it's sort of like definitely a key word in research in tissue engineering at the moment. It's the stage that we are currently at. It has been demonstrated that we can produce a scaffold, we can provide an environment where the cells will quite consistently grow, okay, and create a cellular matrix. We can understand at least a bit about how the strength of that, if it's a bone, for example, how that strength will change over time and eventually strengthen into proper bone structures. But what we haven't really been able to do is to say, okay, can we actually build proper bone in a significant volume ratio? So we talked about the skull plates and the burr plugs that we put in the skull. The thicknesses of those are pretty thin, they're probably less than 5 millimeters thick. So vascularity in a situation like that is not a problem, because you can apply the nutrients externally. The cells can penetrate sufficiently into the scaffold and stay and survive. But what if it's, 20, 30, 40, 50 millimeters thick? Then we've got a problem, because we can't seem to penetrate very well into the actual scaffold itself. So this kind of work is what's currently going on. So here, I think what they've done is that they're being able to introduce some kind of loop into the scaffold. See this black line? So that's a vascular flow, essentially. So they're able to pump fluids through there, which will help with the cell nutrients, help with removal of waste products, because when cells connect and grow, they produce waste, and they have to be removed as well. So that's another purpose for vascular flow. It's not just to provide the nutrients, to provide the oxygen, but then also to flush away the waste products as well. So this is what we're trying to achieve here. So that's the sort of status of which we're able to get. And it's kind of working, but there's still quite a lot of work that still remains to be done in this way. How do we introduce those vascular networks? How do we introduce them in a truly biomimicry or biomimic fashion? Because even if you look at that loop is not presented in a way that you would normally see in a bone or other types of tissues. So we still got a lot of work to do. This is not tissue engineering. This is more implantation to help tissues to repair themselves. I think the reason why David put this in his presentation was because of this case. So this is quite a famous case that was dealt with about 2.5 years ago by the University of Michigan, a young baby that was having problems with bronchial passageways. Similar to the magic arms example, the solutions that were available were too big for a baby, for a child. And so we're talking about an element of customization here and producing a support. So I think what it is that it's really just a protective armor for the standard bronchial passageway. So I think what you've got is you've got a collapsed passageway here, and because of all the pressures in the body, it's not possible for it to recover. So by placing a shield around it allows it to recover and then eventually strengthen to the point where it's not necessary anymore. So I think that that's the kind of point here. I think the other thing for what David is sort of pointing out here as well is that obviously this is the entry into the lungs, and what we're currently working on is probably a resolution where you've got the main bronchial flows, but then when you get into the actual lungs itself, you've then got this sort of double passageway system of oxygen, air coming in through one set of passageways and blood going in through another one and coming into close contact so that you've got exchange of oxygen between the two. So this is through permeable layers and things like that. And in order for that to happen, your passageways have to be extremely narrow. Otherwise, you'll get blood leakage into the oxygen, the airways, or vice versa, both of which are not very good. We've actually seen this already. I mentioned it the other day when we looked at the heart and the hydrogel method. This is quite a common approach these days. So what is referred to here as biopaper or biopaper gel, it's a support mechanism. It's basically just a material that has that can be constrained, but is also flexible. So it's a gel. So we've all eaten jelly. That's basically what it is. It's just a jelly that is a soft, not fully set jelly structure. So that when you then insert a needle into the biopaper and then inject a spheroid of bio-ink into that region, it stays there, at least temporarily. It doesn't disperse amongst the entire biopaper. This provides an environment which enables you to create a three-dimensional structure. If you noticed in this method, they're doing it layer by layer. If you remember when I showed you the image of the heart, the miniature heart that was being made, it was actually a cube of gel, and you were inserting the needle into the gel where you wanted it and injecting the bio-ink. And in fact, there's no reason why you can't do it that way, but in preference to this, or this one's a better way. I was thinking of something else there. Oh yes, yeah, so the biopaper gel has this property, as I mentioned before, of self-repair. So it's a material that when you penetrate it, you inject it, you then remove the needle, the gel then reforms itself around the bio-ink so that it's essentially repaired. Okay? That was the other thing to mention. Why am I talking about this one here? Because this looks a bit strange. You're talking about conductive devices and conductive inks. We've already established that such things are possible by using carbon-based, silver-based, and other types of conductive material, inks or polymers in this case, which has therefore demonstrated it is possible to create some kind of electronic circuitry within the 3D printed structure. As we already established within the bioprinting domain, it's very common to have many heads working and delivering different materials to the same site, and therefore commingling those materials. One of those materials could be conductive. Equally, another material could be an insulator, and therefore we can produce a circuit, and then the possibility of a bionic ear is not completely out of the question. So this is the idea that a lot of people are working towards, and why embedded technology is a useful thing. Obviously, this is not done the way using the previous method. This is just purely by inserting some kind of electronic coil inside a gel mechanism. A lot of the bioprinters prefer to work, or a lot of the people using those bioprinters prefer to work with flexible materials rather than the more rigid materials. And so silicon rubbers are quite common, really to sort of replicate or mimic the cartilage and other sort of tendons and the like sort of behaviors. Something which I haven't mentioned very much up to now, except in the form of using ceramics as fillers within a polymer blend, is the use of ceramics. Now, we all know that hydroxyapatite is quite a common material that's used for direct implantation. There's a number of companies that produce cochlear devices for ear inserts, the basic bones inside the ear, using hydroxyapatite in place of the actual bone. So there's nothing wrong with using ceramics. Ceramics are great materials. Bone is a ceramic. Okay, it's a calcium phosphate base. It's a ceramic base. So there is no reason why we can't put ceramics into the body. There's quite a lot of ceramics which are specifically designated for implantation into the body. And a lot of those are quite easily accessible, including glass. So there's, for example, bioglass is quite a common, is a material which is commercially sold as an implantable glass. Up to now, there has been really no proper 3D printer that creates reasonable ceramic parts. For a while, there was a company called Phoenix, which was a French company that was trying to make ceramic parts. Became another one of the 3D Systems empire. That machine in a lab environment was able to create ceramic parts, but with not any real degree of success or repeatability. And the technology is being shelved. They're concentrating on metal printing technologies. The most effective way to use 3D printing to create ceramic structures is this. Is the way that's described in these samples here, is as a powder filler in a standard 3D printing process. The most effective is a stereolithography or photocurable resin process, where you mix nanoparticles of ceramic in with the resins. The resins you then photocure in a very similar way to a standard 3D printer. Obviously, they're quite a lot thicker in viscosity and things like that, so there are materials handling problems. And then what you do is you take it out of the machine and you put it into a furnace to burn away the resin and to sinter the ceramic particles, usually under vacuum, in which case then you get a shrinkage factor which is reasonably controllable. And I've seen some very, very nice results from machines like that. The Lithos machine on the right from Germany, it's probably one of the best ones, but there's a few others. I'm currently discussing with a company called Admatec, which is also a German company. Seems to have even better results than this, but we're still looking at it. Surface quality is fantastic. The crispness of the designs are great. They're fully sintered ceramic parts, so they've got great functionality, and so they could be used in suitable applications for bio applications. So just worthwhile mentioning at that point. Good question. I mean, I think that because of the temperatures that you're talking about with the ceramics, they will be burnt off quite significantly. Char. I have never seen that, but I suspect you're right, and that you probably have to wash them with some kind of fairly aggressive solvent material. But I've not looked into it sufficiently to confirm whether that's necessary or not. It's a great question. I'll ask it when I go back to find out. But yeah, I suspect there is a possibility that this happens. It may be that it vaporizes, because if we're talking about a polymeric material which starts off as a monomer, maybe you supply sufficient energy, you turn it back into a monomer which can vaporize, and therefore leaving no residue. I suspect that contaminants are actually exactly that. They are contaminants, so they are not the resins themselves, but stuff that might be in the resins. Yeah. Well, plastics Yeah, so they got lots of hydrocarbons in there, and I suppose, yeah, you're right. Carbon contamination probably not a big problem for biostructures, but obviously you want it where you want it. It's a good question, and I have no real answer to that, but it's worth looking into. And just like I said, you know, when people were saying, well, what is it that people are actually researching into, what's their chosen materials? There are so many of these materials. You know, there are, in the hydrogel sector, loads of them. I mentioned already, collagen-based, alginate-based, chitosan, can all be presented in gel structures. The gels can themselves form part of the structure, the final structure that you want, or they can be a support structure for your bioinks and therefore want it to disappear quite early on in the process. It really depends. There's so many different ways and approaches to try this. Like I said, nobody's come up with the golden bullet yet as to which is the best way to really deal with how to create tissues. And we've already established as well that different tissues require different environments. Okay, some want calcium in there, some definitely don't. Some, you know, so there'll be others, you know, there'll be, I guess, some which will, like, you know, related to blood vessels and things like that, might want ferrites in there, or other types of materials. You know, we're pretty complex things, humans. And yeah, and so, yeah, the same applies in the other sectors. Polymers, ceramics, bioactive additives, you know, your growth factors, those which help with the signaling to the cells, to stem cells, to cause them to differentiate, all of those things. So many different ways to achieve these things. So you guys, if you're looking at that as a research direction, you've got plenty of opportunities, and you're not going to be out of a job in the future. Okay? At least for another generation, I think. A bioprinted 3D printed part. What material would it be? Yeah. Sure. I agree. And I can tell you, when I first started looking at this, I was very, very naive. This was when I was still working in Hong Kong, and I had a student who wants to work in tissue engineering sector or this area. I said, oh, okay, well, try something out. And so she spent some work in the lab, and about 2 or 3 weeks later, I got a complaint from the lab supervisor that he had to fumigate the lab because the smell was terrible. And it was really because, you know, we had no idea what it is that we were getting ourselves into. So if you're just making scaffolds without any bioactive elements in there, without any cells or other factors in there, you don't need a clean room. I know that. We've done it because you sterilize the part. Okay, so I mean, you need to be careful about avoiding contaminations and the like, but you don't need a clean room. So it really depends. You know, some of the machines nowadays are quite heavily sealed off, so they're essentially their own clean room. So long as you, at the interface where you deliver the materials are clean in your processes, you can create some results. Potential for contamination is still there, but you could probably do sort of level 1 types of experiments. So you've got levels above that where you definitely need significant clean room environments. So it really depends on where you are in your learning processes, which stage you are in the actual experimentation as well. So I can't answer your question, because you can start off creating simple scaffolds for a few dollars, you know, but then you could, you then do cell regeneration, and then all the equipment you need to look at that, to do the analytical side of things, can cost you millions. So this is why you've become part of a collaborative effort. These days, a lot of these researches cannot be done in a single location by a single group. Very few labs in the world that have that capability. Maybe none. All right? They're all working with other people. If nothing else, to validate. I suppose the only ones are probably the military labs who want to keep everything secret. Yeah? But if we're talking about, you know, standard university and research institutes, they have to work with others these days. So you look at what your capability is and see whether it is possible to feed into some study somewhere, fill in a piece of the jigsaw with another group. You know, and it's not that difficult a thing to do, because it's not just about facilities and resources, it's also about training, knowledge and education. Your background is as important as your equipment, because, you know, I've worked very closely with Dietmar Hutmacher. He's a very, very clever guy, but he's got no engineering understanding whatsoever. Not outside of bioengineering. That's his choice, because he surrounds himself with people like myself who provide those spaces in the equation. So here I was sort of saying that in the tissue engineering space, and you were answering this question to whoever it was that was asking this earlier on, what is what are the critical aspects of tissue engineering? Well, some of it is the material. Obviously, you're constrained by those materials.
Now we are talking bioprinting from last 5-6 years. We are talking about the bioprinting doing that, and like many things are coming into this. Currently, if we talk strictly even for the medical area, for the implants, still certifications are not up to the mark, standards are not up to the mark. There are no set of standards.
Well, I disagree with that. I don't think that's true. What you're saying is that they're not up to the mark from a medical perspective.
Yes. I'm talking about medical perspective.
Yeah.
Whether the standards are evolving or whether they started or like.
Oh, they're definitely evolving. But the thing is that when you talk about standards, the standards within the bioprinting, I mean, there are standard tests you do to identify what cells there are. There are standard protocols that you use in order to fabricate your scaffolds. There are referenced materials in the top journals all over the place where when you read the journal and say, oh, that's how they did that experiment, I can relay it to mine because I understand the procedures and the standards in there. But the thing that you're saying is that it hasn't evolved to the extent that in relation to implantation. I agree with you. They haven't, but they are evolving. Because even there are standards associated with, say, animal implant experiments, for example. You know, if you want to do a rabbit test or a sheep test or a mouse test or whatever, there are standards on how many animals you do, how you treat the animals, what are the time durations. So there are standards. So it's not true to say there are no standards. It's just that they haven't got to the stage because nobody is really doing that implantation yet. I agree with you because, you know, the stuff that you're doing with Dr. Chitra and similar people, they're still sort of having to deal with this through their ethical approval boards. And that's very true. That's the way of getting around the standards because standards don't exist for a particular set of experiments. Sense? Okay. Right. So, as I say, basically these are the three areas that we're kind of revolving around, if you like. Materials, matrix, and viscosity. And probably the interesting one is why viscosity. And so let's deal with that last. Content is obviously in relation to how biocompatible it is, how effective it is. Whether the scaffold or whatever it is that you're creating has sufficient strength. Matrix is usually about the bioactive component of all of this. You know, why low matrix content may not survive removal from printer. Probably high matrix content actually may not survive removal from printer. But basically, the matrix material, the matrix material is the holder, is the scaffold. Sorry, I'm just confusing myself here. So that's the structure. If you put too much material in there, then you may end up with something that's not very bioactive, too little material, and it may not be strong enough. The material content, I guess, is the opposite way round. The viscosity is about just the processing of that material. Because ideally what we want is ideal conditions in viscosity, matrix content, and material content. Because we are constrained by this kind of viscosity equation, which basically means if I narrow my nozzle down or I extrude through a longer nozzle, I am going to have more problems extruding the material itself. So there's lots of viscosity equations, so don't worry too much about that one, about the validity of it. But they all kind of conform to this sort of inverse quad rule, which is the radius of the nozzle, and conform to the length of the nozzle. And then they relate to, you know, viscous relationships and whether the nozzle itself is tubular or not. So if it's a constant radius tube, then you get an equation like this, and P is the pressure. So you continually having to, if you want to do finer and finer detail, you have to provide higher and higher pressure. Until it's, to an extent, you probably do get a cutoff, because this is probably not a complete equation. There are probably some shear-based equations which are ignored until you get to a certain level where they start to become dominant and important, and essentially provide a pressure wall. So you can even, you might have a very small hole in your surface, and there's no leakage because it's so small that the fluid resists itself from escaping. And this is obviously problematic because we want finer and finer detail in our designs. When we started looking at the osteochondrial implants and started looking at the cartilage layers, there's about 10 layers, distinct layers in the cartilage region where you translate from bone to fairly continuous cartilage. And the layers are deliberately cross-aligned so that you've got this sort of weave effect that you get similar to composite weave structures as a way of strengthening the supports beneath the cartilage. I mean, so it's the same as the model for skin. You start off by thinking it's a relatively simple collagen structure and then end up with something that's extremely complex when you look at it in a micron and submicron scale. We do not have printing technology at the moment that matches those scales. So we've got to come up with better. So this is an engineering problem as well as a biochem problem. Okay? And a lot of people's answers to this would be the self-replicating approach, where you provide the environment for the cells to create those structures themselves, because that's what they're designed and programmed to do. That's a great way to do it, but we still don't know how to best create those environments. So we've still got a lot of work to do. I think that's about it. Oh yeah. And yeah, I mean, this is just an acknowledgement that these problems don't just exist in the bioprinting sphere. They're problems that we encounter all the time. So space, i.e. dimensions, providing sufficient porosity, sufficient space for nutrient delivery, this vascularization and problem. And then the other side is time, the growth of these cells and how long it takes. You know, you've got, before a baby's born, it's 9 months. There's a lot of growth in that space. And then it takes another 18 years to grow to adulthood. And even then, after that, we've already established we're still able to regenerate ourselves to a certain extent beyond that into old age. So how are we expected to do this artificially in an accelerated time frame? Because that's what we would want, isn't it? You don't have somebody who says, okay, there's a baby, all right, we'll start printing him some legs because when he gets to 70 years old, he's going to need some new legs. Yeah? That's basically what we do at the moment. Not literally, but as human beings, or at least 20 years. We're probably talking a 20-year period at the moment to grow organs using human beings. So if we want to do it artificially, is that what we're actually thinking about? Are we setting up laboratories where we create organs and grow them over periods of months, years, and then deliver them? I suspect what we would prefer is if it was done a lot quicker. So time is definitely a critical issue. Because this is the kind of thing that we're looking for. We want to be able to, somebody comes in with a cut severe lesion on their leg and be able to then snap on a cell printer and repair the leg or the eyes, you know, or is this is more of a surgical thing. This isn't about printing as per se, but you know, we've talked about this in various instances over the last few days, that this is what people would like. How far away are we? Sorry? There are people doing lenses. I'm not aware of people actually trying eyes. I suspect that's probably one for a little way down the road, because the receptor system, the nervous systems, they're extremely complex, and we're having trouble doing individual nerves. What about then you want to do nerve masses in the eye, ocular nerves and stuff? No, I think it's a long way yet. Okay, so I think we're done there. So, what time are we supposed to finish? 1? Or 1:30? 1? Okay, so we've got 45 minutes. Good. So, what shall I do next? I've got a couple of sort of relatively small, short presentations. Let's do this one. This is just sort of supplementary, perhaps, to some of I think what Prof. Krishnanand did in relation to medical scanning technology and how that relays to what we're doing. From an additive manufacturing perspective, the obvious thing is we want three-dimensional forms. How do we get those three-dimensional forms? The most common technique is CT, as we know, and this is essentially three-dimensional X-rays. Okay, cool. I should switch off the internet here. Mind you, I've been showing some presentations, haven't I? Anyway, the X-ray method has basically been the same since it really started. You know, we detect the X-rays. The amount of X-rays are determined by the density of the object that it's passing through. X-ray is very short wavelength radiation, and therefore can pass through lots of materials and is attenuated by the density of that material. Hounsfield was the first person to able to sort of rationalize that in a numerical, quantifiable fashion. So the Hounsfield unit is basically the measure of attenuation of the X-ray, or the measure of the intensity of the resulting image. And we rely on the fact that, you know, bone is a higher density than soft tissue, and then we've got basically two major types of CT. Sort of a fan mechanism where the radiation goes in essentially a line, and then either is transferred across the subject or spiraled around the subject to create the three-dimensional effect. Cone beam basically is a two-dimensional projection, so it's a bit more like a standard X-ray, but then the cone moves around. So that then gives you that three-dimensional effect. So you've got something like this. So I think the one at the bottom there, that's a more standard CT, where essentially you can imagine that as this ring passes over the subject, you've got a rotating source and detector around that. This one's a little bit more compact. This is a cone beam. So the detector at the top there, and the source here. So it's fanning out there, and therefore you are detecting a larger region. Both of these essentially require you to take multiple images from different locations and then correlate those images so that you can create a three-dimensional map. So you can either present it as a sequence of just X-rays looking in any direction, so that you can say, okay, I'll slice it this way, or I'll slice it this way, and I can view it this way, from the top, whatever, or combine it all together so that you end up with like a three-dimensional image. Both of these, I think, yes, both of these output images are actually from the visualizers on the CT machines themselves. So many years ago, the software Mimics was created initially as a translator from CT to three-dimensional data, essentially STL. Nowadays, that's not necessary because within the machines themselves, they are perfectly capable of creating three-dimensional images and visualizing it and presenting it whichever way you like. The early days of CT was really just saying, okay, I'd like to view my subject from a particular angle. So it wasn't really thinking about presenting it in 3D. It was just multiple viewpoints, so that the surgeon can then home in on a particular viewpoint and say, okay, now I understand what the problem is. So it was really quite interesting. Although it was a knowledge that, yes, you're creating a 3D image, the manufacturers like GE and the like didn't really think of this as creating a 3D data set which for visualization. Well, only when something like Mimics and 3D printing came along, which then realized that you could turn it into a physical representation of that 3D image and visualize it. Because CT was around quite a long time before mass computation. So it's an interesting development. And the other thing was that every CT manufacturer had their own standard, their own format for representing the data and storing it. And so the other thing that Mimics did was take that data format and translate it so that you can then standardize it. And now we have DICOM, which is a standard in its own right within the three-dimensional medical imaging. So Mimics itself has had to evolve. So it started off as a translational software. Now it's a surgical tool and planning software. And you have things like this then. I don't know if 3D Doctor actually is part of SolidWorks. I kind of got a bit of conflicting information from the web. I'm not sure whether SolidWorks is also used as a driver within 3D Doctor, so it's a sort of an add-on to SolidWorks. But 3D Doctor has been around for quite a long time. It used to be free, but not anymore. unfortunately. But it is quite a reasonably priced software. There are others, say here, the ones at the bottom here. There's the Realize, which is more of a service than a software. It's actually a company that uses the data to create, and they have a lot of their own in-house software. There was a company called Anatomics in Australia. They went that route for quite some time as well. They stopped doing that and focused just on making implants. But this is the kind of things that we use the data for. We've already established it's possible to do segmentation of CT in the soft tissue region as well, but distinguishing quite a lot of the tissue types is pretty difficult in CT, and therefore the preference would be for MRI if you're doing a lot of soft tissue or high resolution work, particularly in the soft tissue domain. We talked about cartilage regions, for example. CT, it's pretty difficult to separate cartilage from bone. It's possible with some fairly high resolution and high sensitivity CTs, but it's still a difficult thing. You certainly can't use a CT to the level where you can see a gap in a cartilage in, say, a knee socket. Now, the reality is, and I'm sure you can confirm this, you have, was it synovial fluid, which is basically a lubricant which separates your joint out. So there's definitely a gap between one side of a joint and another. Can't detect it on CT, but you can on MRI. So you can actually see it to that level of precision. And the reason behind that is because it's able to tune in on different molecules. And those different molecules correspond to different tissues. And therefore, it's possible to sort of track all of that down and identify the different tissue regions. So you can get really high definition. So I mentioned here, so we've got a nice picture, and it's not actually that brilliant a picture, but I can still see here, sure, in the original, you can see the gaps even more clearly. I can see some gaps in there. The top one there, that's, say, very high resolution MRI scan. This one, functional MRI, which basically requires you to sort of track molecules which are injected into the body. And so you can sort of see how they move around the body. So you can look at blockages and what goes on in the brain, and whether different stimuli affect different parts of the brain and stuff like that. So there's lots of exciting things that can be done. Obviously, a lot of these don't really need 3D printing. It's not that CT and MRI was made and is just used for 3D printing. There's all sorts of purposes, and the technology has developed immensely over the years. Okay. Mentioned a little bit about ultrasound as well, and I think those of you that have been involved in parenthood probably wonder what I'm talking about, because whenever you get an ultrasound image from your doctor, I kind of used to find quite difficulty actually working out what the image was. This was like when I was having kids, which was like 30 years ago. I've noticed that ultrasound imaging is a lot better these days. A lot more noise removal, a lot better fidelity. But the images are still pretty difficult to interpret. But that's really because we tend to look at it again as a two-dimensional issue. And in fact, again, it's more of a three-dimensional sensing method. And the way here is, in fact, they more refer to it as ultrasound 4D, because the real good images are generated by combining multiple images together to help you with noise removal and to help you with combining and registering them all together. So there are a number of examples where you can get really quite good detail. Good friend of mine who's in Brazil, his name's Jorge Lopez, is quite famous for this, doing work in this space. The lady on the left is a mother. She's still pregnant. She's still got ready, not delivered yet, but she's blind, and so therefore she couldn't see the ultrasound images anyway. So what George did is he worked with the ultrasound group and stuff like that to create a 3D model. So this is a tactile model of her baby before it's born. So she was very appreciative of that. In a more widespread application space, you can also do some diagnosis before delivery of the fetus to just see whether there's any potential problems that might occur during delivery or with the child once it's delivered, so that they can be ready to treat it, or maybe even treat it whilst it's still in the womb. George is also quite famous for a number of other reasons. His son, as a fetus, is on display in the Science Museum in London. So he was part of a project where they did this, and he was telling me a story of when about 10 years later, or maybe 8 years or something like that later, he took his son to the museum, and they had this sort of press reception, and his son was not happy that he was on display as a naked baby, still in the womb. So he was a bit embarrassed by all of this. So he was telling me that story. And the other thing that he's also quite famous for is he's a curator. He was a curator for the museum in Sao Paulo, the one that burnt down late last year. So one of the actual bright, or that was a very sad event, and lots of very priceless exhibits were destroyed. But he'd actually done quite a number of scans. So there were a few mummies, for example, Incan mummies from South America that he'd already scanned, and he had the data set. So he reproduced some of those, which was some consolation, not a huge amount, I admit. We also mentioned, we looked at the stuff for Scott Summit this morning, Bespoke Innovations, where he is reliant on body scans, external body scans. There are a variety of ways to achieve this. Laser scanning is one of those. Not necessarily the best way to achieve a scan of the body, primarily because of the lasers themselves. Wouldn't want to scan people's faces unless they've got their eyes closed or have got some covers over their eyes. Although the lasers are not that strong, that powerful, it's really about the precise wavelength, and therefore the the filtering that can be done on the laser. So they're not high power lasers, but all the same, wouldn't want, bless you, they wouldn't want that to happen. But you can get very good fidelity. This is actually, anybody recognize this? It's the Natural History Museum in London. That's a scanning of it. You've got to be somewhat careful about scans that look like this, because that is actually not just a scan, but a scan plus a rendering. So what you usually have is, yes, you've got the laser and the triangulation or time of flight method for measuring the distance, but then on top of that you have an image. So what you've actually got there is a captured image which is overlaying. So anybody that's played video games will understand the difference between the geometry and the texturing. So this is, the image there is actually texturing. So it's difficult to establish what the absolute precision of this scan is. What sort of level of detail are we actually talking about in terms of scanning resolution, distance resolution? Obviously it's a function of the actual distance itself and the width of the image. But we can scan at a body level to sub-millimeter, sort of in the tens of microns without too much difficulty using this type of technology. There are alternative methods to this which might help us a little bit with the facial imaging. For smaller objects, sometimes it's better to use this kind of method, a structured light method. Basically what you're doing is just triangulation. So in other words, you know where if you had a flat object at a particular distance, what the spacing of those fringes would be and the location of them. So it's not difficult for you then to translate that to the image if there's an object placed in front of that, which will help to look at the distortion or different deviations from the original image. And this is quite easy to do. So this is a very low-cost device. You can do it for a few hundreds of dollars, where this is what's providing the projection. So it's a very simple data projector, and then a couple of fairly reasonable quality cameras. And then the other side of this is that you've got, as well as the structured light, you've got more than one camera, so you're looking at it at an angle, and so you do the calculations. So it's pretty straightforward method, and can give you very good fidelity results. With the projector, you can even move the fringe pattern or change it to a grid pattern. You can go from horizontal to vertical, all of which will help you to build up a more precise model. You need high contrast. You don't need a dark room, because it really depends on the quality of the cameras. The cameras are not grayscale, they're color cameras, so you can do filtering and other methods to help you overcome those effects. But yes, you do need a controlled light environment. The better you can control the light, the better the scanning can be, 100%. But you don't need to have such a fine level of precision, because you can even do it in normal light using a photogrammetry method. You don't need the projected stripes. The projected stripes just help you a little bit with the registration and the like. So this is an image where maybe the surgeon, I've worked quite a bit with dermatologists and looking at skin defects, looking at moles, cancer, blemishes, skin cancer, other types of skin problems. There's a lot of interesting work that can be done in that space. Nowadays, a lot of the dermatologists, they usually also work a lot on hair restoration as well, but use even 3D full body scanners like this. So what you saw in the previous example was just two cameras, and you're just purely doing a triangulation between the two cameras. And as you move the camera around, you can build up a larger surface area, and that gives you the depth effect. And the resolution of the cameras is pretty high, and so you can get good depth effects. One of the projects that I was working on with a dermatologist in Melbourne, he had a scanner similar to the one in the bottom right there, where somebody can just basically go into the scanner, hold their hands out wide, you know, like the ones you see in the airports. You have to do that, don't you? And in 2 seconds, you've captured the entire body. And what the software on the systems were able to do, because you do that, obviously you've got somebody who's mostly naked in there and you're capturing all of the skin in there. And so what the software does is it filters out where are all the, so it's got recognition software, so it tells you, this is a mole, and it puts the biggest mole first and then the smallest ones and things like that. And then what the surgeon wanted was for us to then hack that, which we were able to do, in fact, in order to get the three-dimensional data, because he was just looking at it in terms of a body map. So, in other words, he'd get a list of all the moles, he'd look through them, he'd click on one, and then that would tell him where that mole was on the body, which was all the three-dimensional part of it that there was. So the benefits of the scanner was you take the entire body in a couple of seconds, and then you can correlate whatever you see to the body very quickly, so that then the surgeon can say, okay, I want to look at that model, tells it where it is, it's on the arm, so the guy then will look at it on the arm and then do a closer diagnosis. What he wanted to do was actually to be able to maybe map the texture of those moles as well, because he said that a lot of diagnosis was also based on feeling the mole. And remember that we were using the object Connex printer, which is able to do soft and hard materials. So we were printing off examples of moles so that you could look at them on the screen and you could touch them. So it was, for this, it was a training aid for his students. So he could say, hey, this is what it looks like, and this is what it feels like. And so we were able to create tactile models for him. So there was a few other things like that. We were also taking the data, because it's mapping a three-dimensional data, and one of the other things that this guy wanted was to be able to create a more realistic wig. He was actually made wigs, and the more realistic of the wigs relate to where the actual hair follicles should be on the head. So we were able to map where the hair follicles should be on the head, so he could then replay that in the wig making process. Yes, what else? So this is just another one. Dental CT. So, you know, when you're specializing and you only want to look in a space that you know is in this sort of region and this sort of size, you can build a CT machine to match that requirement. I think one of the examples I had of conventional CT was actually an industrial CT image, where you can use high intensity X-rays to create a 3D image of an object. So it's not just limited to bone. You can scan pretty much anything with X-rays. And so industry also uses CT imaging as well for objects, particularly reverse engineering objects which are made of metal. And you can penetrate into the metal and see through it and see what's inside it as well. So I think one of the reasons I put this up is not so much because of this, dental CT, being able to provide lots of 3D info, which can then relay back to how you make all of these dental implants. Remember, we kind of identified that dentistry is one of the most profitable and most active regions in additive manufacturing. So this is partly because we can also access and generate lots of data from it, and it's quite a common process for a dental lab to have, or at least a central clinic to have a dental CT, you know, where you can refer somebody and they can create those images, and therefore you can use that data in a very efficient and effective manner to create your implants. But remember, I also mentioned about Invisalign yesterday, and I showed you the video, and some of you might have noticed this. Okay, this is the iTero scanner developed by Invisalign. I suspect it's a company that they've been working with. So this is a great starting point as well. And this then becomes even more accessible, because I'm sure this is much cheaper than a CT scanner. Because it doesn't do everything a CT scanner does. It doesn't penetrate into the bone and show you the root system. So it's not helpful from that perspective for doing dental surgery, but it is perfectly adequate for the Invisalign process. And it does very, very well, and it's very, very precise, and it can map your teeth alignment quickly and easily by basically what happens is that the nurse moves the wand around the mouth, gradually building up this image. So the image basically is built up in real time, and if there's a gap, then the nurse can then put the wand closer in there and capture more data. I suspect that there is a registration method. Probably there's something that is inserted into the mouth which relates the geometry of the mouth to the wand, but it should be a relatively straightforward process to create that sort of image. Okay, so 1 o'clock? Yeah, you've got a question. You've got 10 minutes.
Okay. So one of the major challenges regarding the 3D scanning is the images created, the model which we create is the hectic process of the post-processing. So in the market, is there any 3D scanner which makes a good model which can replicate the manual modeling part?
Right. Well, so there's a couple of answers to that question. There are lots of different types. In the optical scanning space, yes. So let's start with that. So let's look at surface scanning versus penetrative scanning. So the laser scan optical scanning versus CT MRI, okay? So let's talk about surface scanning, which probably I know more about anyway. There are methods which help in the scanning process. So for example, this is why a lot of the scanners have markers which you place on the object. So all of those things are there to try and help you to eliminate some of the, so you put a reference point, and so that allows when you move the scanner around, you can relate to the reference point, etc. So that's one method, and there are similar methods to that. There are, for example, scanners which themselves are scanned. So you have a static scanner and a mobile scanner. So the static scanner tells you where your mobile scanner is and relays the image, the image that the scanner sees with its location. So a lot of methods like that. Okay? So there's that. Then, in addition to that, there is a lot of what we call reverse engineering software. One of the most famous is probably Geomagics. Basically, taking all of that scan data, which is usually what we call point cloud. A lot of scanners now, in fact, can do better than point cloud, but we generally say, okay, what you've got is a mass of points, all of which are a distance in three-dimensional space. So the first thing in CAD you need is to map all of the, mesh all those together. So the reverse engineering softwares, that's what they do. They do all that meshing. So they take all those points and then join them to all the next points and gradually make a mesh. Now, that's a large piece of data. And if you've got a flat surface which is measured as purely flat, and you've got 1 million points on that surface, you can really represent it by just half a dozen points. So a lot of what the does is data minimization as well. So there's that kind of thing. So there's a lot of tools around which help you to do that. Most of it is interactive with the user because what some people see as noise, other people might see as actual objects. So it's also very much open to interpretation. Now, go on to the softwares for scanners, for CT, MRI scanning. There's a lot of software which essentially reflects that as well. So this is why you've been looking at Mimics, Magix, 3Matic. Matter of fact, I've got a presentation. I won't go through it entirely because you'll shout at me because you want your dinner. But let me just start it up. Okay, let's just start with this one as a bit of a teaser. I'll be talking about this tomorrow. So Materialize have a whole range of tools, one of which is this one called OrthoView, which is one that's not so well known, that's why I put it up here. So you get this kind of image as standard, sort of typical from your scanner. So there's a lot of edges in here that look like sharp edges, but when you look at them in more detail, they're not very sharp. And so there's a lot of interpretation of these kinds of data sets, which are largely driven by your knowledge of anatomy. So there are now tools which are sort of largely labeled as AI, artificial intelligence tools, which are able to take an image like this and start to extract some additional knowledge from it to say, yes, this is whatever, a femur or a pelvis or whatever, or the regions, and then say, well, okay, this is what I would normally expect, and this is what I see, and I make a comparison, and so I tell you where I think the pelvis actually starts and where it ends, or one of the spinal processes starts and where it ends. So, you know, there's a lot of expertise incorporated into this as well. So this is an area where there's a lot of growth at the moment, is AI, data management, what we also can label big data or machine learning, where we've got a lot of these images now. So machines can now look at all of those images and then start to extract what is the commonalities between them, and therefore recognize them in new images. So there are a lot of tools. It's getting to a point where, yes, you can descend. And the reason for ortho-view, so this is the reason I put this one up in particular, is because this is kind of like an AI-driven version of Mimics. So this is materialized software as well, but it's not at the level where you play around with the data. So it's kind of saying, all right, you tell me roughly what you're looking at, and I'll fill in the spaces. And then what I'll also do is, so this is obviously some kind of dynamic hip repair mechanism that's being put in here. I need to know where the plates are going to go and look, and what that might mean in terms of the screw insertion. So all of this is a visualization tool that the surgeon can play around with prior to surgery to ensure that there's no surprises in the process. So I don't know if that fully answers your question, but yeah, there are a lot of tools there. Okay. Lunchtime? Okay, so I think I'm free for the rest of the day, I think, again. So I'll see you tomorrow. You'll be really glad to hear I've done all the exam questions, and they're all ready for you. I don't know when it's going to be. I think it's after lunch tomorrow. Yeah, something like that. Yeah? Oh, you're going to make an announcement. Sorry. Oh, I'm sorry. I spoiled your thunder. There you go. Thank you.
Thank you for your excellent lecture right from the morning. So the announcements are, one announcement is regarding today's afternoon session after the lunch. There is a slight modification in the timetable which we have given to you, and there is a lecture on oral maxillofacial case studies by me, and then there is a demo on Reno software by Fanindra, he is my PhD scholar, and then that will be, say, yeah, first 1.5 lecture by me, and then after the tea break, maybe around 30 minutes, Fani is there? Okay, 30 to 45 minutes demo on the Rhinoceros, and then followed by a lab visit. Actually, several people are asking to have a lab visit, so then there will be a lab visit after his demo on Rhinoceros software. So that is the one announcement. There is a slight modification in the timetable. And tomorrow, first lecture by you, yeah, and after the first lecture, so again this is the demand from the participants saying that the group photo is a bit of, some people are missing, some people are hiding. So then what I asked the photographer, so he will come again, and then we'll go to the library building, and there will be a steps. So there is no chance of missing. So then there will be a the photo session at That is at 11 o'clock tomorrow. And then, then followed by his lecture, again the second lecture of tomorrow's thing. And after the lunch, there will be an exam who opted for the credits. So when I asked the Rakesh, he said that there are 16 people who opted for the credit certification. So 16 people, and again from the public demand, a lot of people are interested to write the examination. So we doesn't want to curtail your interest. So you can write an examination, but you don't get a grade sheet. But I will announce the key, so you can self-evaluate how many marks you got. So after the examination, I will announce the key, so then you can self-correct. That can be done, but I cannot issue a certificate. The people officially not on the GIAN portal, so it is, some people are done. But anyway, I think it is okay, some extent is okay, right? So you can write an examination and you can self-evaluate. I will read the key with your permission. So I will read the key. Yes, exactly. Exactly. So you need to have some discussion, something you said that yeah.
Some students that were asking about research opportunities.
Correct. Just now, even I got one message. I have forwarded you WhatsApp message, same thing. But anyway, you are ahead. Then okay. So then you are taking care of that also. You want to, yeah. That's the when you want to give that one.
Well, I'll do it within the lecture time.
First lecture, second, maybe.
If I get 2 lectures still,
Yes.
tomorrow, so maybe probably at the
Second one. Okay.
that'll be the last one.
Okay. Okay, fine. So, and then after the lunch, the examination. So the examination, and then we will send the grades afterwards. Let me see, it is possible. Let I quickly evaluate, and then, but fitting the curve, you are all teachers probably. you know the distribution of the marks and giving the grade. Whether it's a relative grading, absolute grading, but anyway, it's absolute grading. Okay, so it may take some time. Let me see, like, if I can do it by tomorrow, but it may not be possible. Otherwise, what I can do is I will post the grade certificate through hard copy through the courier. I will courier the certificate, but your signature is not required on that. I have double checked it. Otherwise, then okay. So this is the thing, and after lunch you are not going to take any class, right? So yours is done. Okay. So then probably we can plan maybe around 3 o'clock the valedictory, the certificate distribution, or maybe before that. We'll see. So maybe it's a half an hour exam. Yeah. Yeah. So 2 to 2:30. 5 minutes. No, even I want to write the exam. Let me evaluate myself. So 2 to 2:30 the examination. Maybe after that, let us see, like maybe valedictory, or yeah, 2:30 or 3 o'clock. Around that we can plan the valedictory, the certificate distribution. So yeah, these are the announcements. Then we'll go for the lunch. We'll break for the lunch and we'll come back at 2 o'clock. Okay, right. Thank you.